Hey, it's Mr. K doing a video for AP Physics 2. We're going to look at some more fluids, and to start off we have these two pipes here. We have one that's radius R, goes to radius R2, gets a little bit smaller. We have one that's of height 1, goes to height 2, and we need to have some considerations as far as all that goes. And so, to think about what happens, we need to talk about what happens to the individual pieces of these molecules that make up the fluid. And so for the one here, if we have 4 pieces that travel to the right to R2, well, they start to get scrunched down, and if we have more incoming, we always have more incoming to push them along, then in order for them to make way, if they're all in a small area, they have to move faster. Okay, that just makes logical sense. Well, for this one over here, if these particles of fluid are going to move up, well, they're going to gain some potential energy with respect to the ground or whatever's down below it, and they're probably going to slow down, or something's going to change with the pressure. All right, so with some considerations there, and to think about all that, we have these new formulas that apply to fluids, and it's going to be right over here. So let's talk about these equations. This first one is called the equation of continuity. This is the conservation of mass equation, and all this says is the mass in has to equal the mass out, and if the hole gets smaller, then the mass better start moving faster. Alright, so the equation of continuity says the area of the first thing times the velocity that's over here is going to be equal to the area of the second part times the velocity that's over there. And so if we go from an area that's related to the radius r1, and if we cut that radius in half, then that velocity should get much faster. All right, and so since we're talking about a circle here, the area is going to be pi r1 squared, and that should be multiplied by v1, and that's going to be set equal to pi r2 squared, and that's going to be multiplied by v2. And so if we just look at what happens here with r1 and r2, r1 is twice r2. So if we were, well, let's cancel out the pi's, those don't matter. If r1 is twice r2, we have 2 r2 right here, quantity squared, times velocity 1 is equal to this second radius squared, v2. And of course this 2r2 squared, that turns into a 4r2 squared, which then results in our r2's being able to be canceled out. And what that tells me is that my velocity should be much faster at the second place. The second place, this velocity over here, is 4 times the velocity of the first place. It's not double the velocity, it's 4 times because of the square in this term. Alright, so equation of continuity is going to help us out there. It'll be comboed up with some other things. The other equation that we have over here is called Bernoullis Equation. And it kind of works off of, it's like a conservation of energy equation if you kind of look at all the pieces. Rho GH, if we were to multiply everything by volume, we would start to get the exact same equation as the potential energy, kinetic energy equation that we're used to. Excuse me. And so Bernoulli's equation is going to help us out with fluid flow that changes height, more like this problem here. Okay, these two equations are going to be used together. There's one more thing that is going to be Bernoulli's principle, or Bernoulli's law. I'm not sure if it's the law, I should really check on that. But Bernoulli's principle, which says, let me write it out. Bernoulli's, I'm going to say principle because that's what I'm thinking of. Not principal, but principle. And it says faster moving fluid has lower pressure. And the idea here is that fluids, in order for fluids to create pressure, they bounce off stuff, they hit stuff. So if we have a box and these fluids, let's say a gas, is made up of all these molecules, and all these molecules, as we know from thermo, are all flying around, different speeds, different rates, but on average, they are flying with a certain speed based on the temperature. And they're colliding with the wall, and every single time they collide with the wall, they exert a force, because that's an impulse. And so that force is going to create this pressure over this area. The force over this area is going to create this pressure. Well, if we were to somehow give these molecules in total a net velocity, then what's going to happen is that, let's say we have another example here, and from thermodynamics, they should be flowing and flying around at very, very high speeds, like 500 meters per second at room temperature. And the sound in the background is Peeps playing with her ball. But on average, if they have this velocity that's more down than up, let's say, there's less stuff that's interacting with the sides of the wall, so the pressure on the sides of this container would start to go down. So Bernoulli's principle says faster moving fluid has lower pressure. So an example of that would be like your shower curtain. If you take a shower, you turn the shower on, that air inside of your shower starts to move around, and that would lower the pressure. But the outside in your bathroom is still the same pressure as before. Holy crap. And so that difference in pressure would result in some force to pull that shower curtain out towards you. Let's see, another example would be the wing of an airplane. The wing of an airplane, let's say it's shaped a little bit like this, and there's a little bit more curve on the top than on the bottom. And so if these particles of air go over the top and over the bottom, or under the bottom, then the distance over the top, this top distance, is a little bit longer than the bottom distance, but you still have to have the same amount of stuff to meet back up on the other side. And so to travel over the top, you got to go slightly faster. All right, and what that says with Bernoulli's principle is that the pressure on top is going to be less than the pressure below. And what that causes is this difference of force, and that's called lift. All right, so airplanes with this little curved bit of wing here would create lift as this air was traveling over the wing. Now, the other way that airplanes create lift is they literally just like have air hit them, and when the air hits them, it deflects downwards, and that downward deflection would cause an upwards force. So that's like an angle of attack thing. But Bernoulli's principle is where you actually have to travel a little bit farther on top than bottom. Therefore, your pressure is a little bit lower, and then you have this lift. That's why these huge airplanes can actually have enough lift to stay in the air. That and this angle of attack thing. Down here, we can talk about the problem. Let's say we have like a sprinkler system kind of set up, and we need to find out some things in this problem. And let's see, what could we look for? We're going to look for the velocity at area 1, so over here. So what's the velocity of the fluid in this pipe? Another question we have is, what is the absolute pressure at this point? And then, what's the maximum height that you can go to? So this fluid goes through the pipe, it raises up, and the area does decrease, so it should get faster. But at the same time, we are raising up, so it should get slower. And so we need to actually combo the equation continuity with Bernoulli's equation that we just saw up here. So looking quickly, we have the area in this pipe, we have the secondary area up here for this little nozzle for the sprinkler head, or the fountain head. We've got the velocity of the fountain head, and we have the change in height, as well as the density of our fluid. It's going to be just water, so 1,000 kilograms per meter cubed. So looking over here, back to our equations, if we want to define the velocity at point A, or A1, we know the area of A1, we know the area of A2, we also know the velocity of the exit. So we're going to use equation continuity here for this first part. So equation continuity would say that the area times the velocity is equal to the area times the velocity of the second point. And the area, let's try to work upwards so we don't just cram everything into this bottom part. The area of the bottom, A1, is going to be 1 times 10 to the negative fourth. The velocity is what we want. The area secondary is going to be 0.5, half that, times 10 to the negative fourth. Those should cancel out. And the velocity, exit velocity, is going to be 8.2. Okay, so if we look at things that we can possibly cancel out right now, that's going to be this times 10 to the negative 4 thing, times 10 to the negative 4 thing, and really it's just going to be half times 8.2, and half of 8.2 is going to be 4.1. So the velocity at V1 should be 4.1 meters per second. Now, pay attention to what happened here. The velocity, or the volume, did change. It was halved, and so that directly halves that velocity. All right, or it doubles that velocity on this side, it has it on the other side. Up here we had the 4 times because we weren't changing the volume directly, we were changing the volume indirectly by changing the radius. All right, so we were changing radius, we doubled that, or we halved that, and that ended up for the velocity change of 4 times or 1/4. Peeps, 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 she's so cute. All right, second, now let's do part B. The absolute pressure at A1, the absolute pressure should be the gauge pressure plus the atmospheric pressure. All right, and so in order for us to get the absolute pressure down here, we're going to have to work some Bernoulli's principle. So working Bernoulli's, we need to write down our P1, the pressure at 1. That's actually what we're looking for. The rho GH, the 1/2 rho V squared, and then set that equal to the same thing for point 2. In order for us to do that, we need to set a 0 mark. And whenever we do conservation of energy, we always set the 0 mark for ourselves somewhere in the problem. It's either at the ground or the lowest point, or for space problems, it's going to be at infinity. So I'm going to set the 0 mark here. Okay, and that says that we have a change in height of 0.5. But it's going to be really convenient for us to work with because Bernoullis equation says that pressure 1, the one that we're looking for, plus rho GH1, which I'm going to call 0, because that's going to be our lowest point, plus 1/2 rho V1 squared is equal to the exact same stuff on the other side. So I'm not going to write it, I'm just going to put those little dittos. So now we can write in some numbers. So P1 is what we're looking for, plus this is going to be 0, because the height would be 0. And then we're going to add in the 1/2 rho, the density, and the velocity. How would we know the velocity down there where we just found it? 4.1, square it, is equal to the exact same stuff, but on the other side, we kind of know the pressure out here, right? And that's going to be the atmospheric pressure. So we'll call that about 101,300. Sometimes we will just use 101,000. Plus the next term, rho GH, 1,000. Now we're actually going to have this term. It's times 10, and then h is going to be 0.5 because we went up 0.5. And all that does is it takes away from the velocity of term. Plus 1/2, 1,000. Well, we know this one. It's going to be 8.2. And that's going to be squared. All right. So let's work some math, work some magic. I'm going to do the right side totaled up, 101,300 plus 1,000 with another 0, and we're going to half that. And we're going to add in, not divided by 0.5, but times 0.5. And we're going to add in half of 1,000 is going to be 500 times 8.2 squared. And we'll subtract the stuff there, so that's going to be 500 times 4.1 squared. And let's see what we get. So the pressure, 0.1, is going to be 1.315 times 10 to the 5th power. And let's see, 1, 2, 3, 4, 5. It definitely went up, and that's what we want. So it's going to be a higher pressure because it's lower, and it's going to be lower. And so the absolute pressure, which is including that atmospheric pressure, because that's kind of what we did over here, is going to be 1.315 times 10 to the 5th power. And then the units would be the Pascal. Alright, last part over here we can do, we need to find the maximum height of the water coming out of the hole. And all that is just knowing the velocity coming out of the hole. That's really it. So we'll just run a little bit of conservation of energy. We'll talk about the kinetic energy of some part of the water. 1/2 mv squared should equal mgh. Or if you wanted to work it with Bernoulli's, you could. It's going to be 1/2 rho v squared is equal to rho gh. And you can see how it kind of turns into the same thing. The height would be, let's see, 1/2 is there. We're going to have that g on the bottom and v squared on top. And that should be equal to h. The m's or the rho's cancel out. And we get, let's see, 8.2 square it divided by 20. And we get about 3.36 meters in height. So to use Bernoulli's equation, if you have a fluid that is moving, maybe it's changing height, you can set up Bernoulli's equation if you knew the pressures. Usually the pressures are just going to cancel each other out. In this case they didn't, because we have some pressure in here, we have some atmospheric pressure out here. They usually cancel out because usually it's atmospheric on both sides. But it really just depends on your problem. Alright, well, we will stop there, and there are more fluids to talk about in the next one.